Good evening, everybody. It's lovely. Well, I can't see you, of course, but it's lovely to see so many people listed. There are over 50 people in attendance already, which is fantastic. Welcome to the second lecture of the Keele Physics Centre Evening Lecture Programme. As those that attended the first lecture will know, this is a first for our particular centre. We've never had to broadcast over the internet before, so bear with us. Hopefully there won't be any technical issues tonight, but you never quite know. And I'll very shortly introduce you to Professor Hirschi, who is giving this evening's lecture. This evening is slightly different, as you might notice. We are very lucky to have Stephen join us tonight, Stephen Bostock, who is signing for us. We've had a request from the hard of hearing deaf community if we could support them in accessing these lectures. And so Stephen's here to help us do that tonight. To help Stephen and those particular listeners, we will be having a short break of around 4 or 5 minutes halfway through the lecture, which will allow the rest of us to go and grab a cup of tea or use the conveniences, of course. And then we will look to finish as we normally do in around an hour at 8 o'clock. Hopefully you can see my screen, which is the current lecture program. As I said, this is the second program in the series. Sorry, second lecture in the series. We have 4 more in the new year, starting with Dr. Mark Worley giving us a lecture on Caroline and William Herschel, moving through to extraterrestrial geology. Those that are interested in geology will be very interested in Natasha Stevens' particular lecture. She's an excellent speaker. And then we'll move on to some data science towards March. So there's lots of interesting and diverse material to get on with. Anyway, so with no further ado, I'm going to introduce you to tonight's speaker. And that is Professor Raphael Hirschi of the University of Keele. Raphael is a professor of stellar hydrodynamics and nuclear astrophysics. I've known Raphael for some time, and I think you'll really enjoy this evening's lecture. Just to give you a bit of background on Raphael himself, he completed his MSc at the Swiss Polytechnic School in Lucerne back in the late 90s, and then completed his PhD at Geneva Observatory 5 years later. I'm not going to tell you much about his research because you're going to hear a lot about that this evening. But all I will say for now is I hope you very much enjoy this evening's lecture. If you have any questions, typically if this was in person we would ask them at the end, but if you have any questions, please pop them in the question box. That will appear on the right hand side of your screen for most of you. If it's convenient, Raphael will answer those during the lecture itself. If not, I will collate them and ask them at the end. So I hope that makes sense. That's the question or chat function within this particular system called GoToWebinar. Anyway, with no further ado, Raphael, I'm going to hand over to you, and everybody enjoy the lecture. Thank you.
Okay, thank you. Okay, can you confirm that you can see my screen? Maybe Stephen, can you see my screen? Sorry.
We can indeed, Raphael, yes.
All good. Okay, so tonight we're going to answer the question, what are you made of? And let me see if this works. First of all, there are many different ways of answering this question. So a child might answer, I'm made of arms, legs, and eyes. A boxer might say, I'm made of steel, don't fight with me. A philosopher might say, I'm made of body, mind, and soul. And a particle physicist would probably say, I'm made of electrons, protons, and neutrons, and protons and neutrons are made of up and down quarks. In this talk, I will talk about the chemical elements we are made of. So if you go on Wikipedia, you'd find the following sketch of a human body split according to mass. So if you look at the left, this is fraction in terms of mass. So you 65% of oxygen, 18% carbon, 10% hydrogen, 3% nitrogen, and something else as well. And you have a full list. And you see that you have different fraction depending whether you consider mass or number of atoms. Indeed, an atom of hydrogen is 16 times the mass of an atom of hydrogen. But the question on this talk is, where do these elements come from? And also, where do the other chemical elements come from? So that brings me to my overview for this talk. As you already know or will know by the end of this talk, chemical elements are created in stars. So I will first give you a brief overview of stars and their properties. Then I will spend some time discussing how we can simulate stars on computers. Why do we want to simulate stars on computers and what can we learn from that? And then how do the stars produce the chemical elements? And then I will end by answering the question, what stars are you made of? Let me just try to rearrange my screen a bit here. Okay, so let's leave planet Earth, go into space to learn more about stars. So stars are quite extreme. If we first look at the temperature of stars, you see in the night sky, stars have different colors, and the color of a star represents its temperature. In this case, red is cooler than blue, and blue is hotter than red. But generally, the surface of stars is of the order of thousands of degrees, whereas the center of stars can be between millions and many billions of degrees. In terms of size, this is one of my favorite slides to show in public talks. The size of stars varies quite a lot. So if we go at the top left here, we can first compare the size of Mercury to the Earth. And then Earth looks quite small compared to Jupiter. Jupiter then looks quite small compared to the Sun here. And then you have different stars with different names. The names come from the people who first discovered them, so throughout history. You see Sirius here that looks good, big, is then tiny compared to the star called Aldebaran. And this star, for example, has a radius that is 43 times the radius of the Sun, which is here on the left. Aldebaran looks tiny compared to Betelgeuse, which is in Orion Nebulae, and Betelgeuse is still not the largest star, which is currently VY Canis Majoris. So this star has a radius 2,000 times the radius of the Sun, and therefore corresponds roughly to the distance between the Sun and the Earth. Okay, another way of looking at stars is how dense stars are. In particular, if we want to find the densest stars, we have to look at what are called stellar remnants, is the core of stars at the end of their life. So if we start in increasing density, we first have white dwarfs, which have the mass of the Sun in the size of the Earth. So this is already quite dense. If we go up in density, we then have neutron stars, which have the mass of the Sun, but now a radius of only 10 kilometers. And finally, we have black holes that have more than 3 times the mass of the Sun and a radius less than 10 kilometers. So since we're in England, it's already winter, or it doesn't have to be winter, but lots of people drink tea. Just imagine you wanted to replace the sugar in your tea with a teaspoon taken from a neutron star. The question is, how many cars have the same mass as a teaspoon of neutron star that you would put in your tea? Okay, so maybe we can see if the chat works. You want to try to guess the answer. So how many cars have the same mass as a teaspoon of neutron star? Just to realize how dense neutron stars are. Yeah, thanks, Scott, for maybe I can answer the question at the break. Seems to take time to use the chat. Okay, next I want to discuss briefly how can we simulate stars on computers. So the first question is, why would we want to do that? And if you look at the night sky, you can see different stars, but you don't see them evolve in time, because the lifetime of stars is between millions and billions of years. So over our lifetime, we don't really see stars evolving. There are some exceptions, but in general, stars look the same every night. However, if we compute a model of the structure of the star and integrate its evolution or make it evolve in time, we can try to predict how stars like the Sun will evolve in the future and what is their fate at the end of their evolution. Now, how can we simulate stars on a computer? Well, we take the basic equations of physics, which are listed here. The first equation represents conservation of mass. The second equation corresponds to conservation of momentum, and the third one corresponds to conservation of energy. And finally, the last one is about energy transfer. And generally, we're gonna assume that stars are spherically symmetric. So we're gonna assume that everything on a sphere is the same. So the temperature will be the same anywhere around on a sphere which has a given radius. So we call these models one-dimensional, where everything just depends on the radius, not the angle along for a given radius. And if you look at pictures of many stars like the sun, it is roughly spherically symmetric, so that's generally okay. However, stars are not exactly spherical. So we can see on some other pictures, for example, if we consider magnetic fields, that we have deviations from spherical symmetry. And there's also a lot of physics going on. So what type of physical ingredients, as we call them, do we need to include when we want to model stars? First key ingredient, which is especially important when we want to consider which chemical elements stars form, is nuclear reactions. These are the reactions and the information we're going to need to find out how hydrogen is transformed into helium and how all the other chemical elements are produced. Second one is mass loss, and this is how radiation, so photon light emitted in the center of the star, interacts with the material throughout the rest of the star. I'm going to then show you simulations of convection and turbulence inside the star, and this is important to know which parts of the stars are mixed. I'll come back to that. Then stars rotate, so this is also important to see how rotation affects the evolution of the star. I've already mentioned magnetic fields. Binary interaction means when two stars are so close to each other that they're going to start affecting the other star via their gravity. And the list goes on. So there's basically a lot of exciting physics in models of stars. Okay, so now, as you know, the world is three-dimensional and stars are three-dimensional. So in my dreams, I do computer models that are three-dimensional models of stars. That means I follow everything inside the star without making this assumption that things are spherically symmetric. And this has main advantages, as we will see later on. We can simulate fluid instabilities in full glory. We can model 3D processes as 3D processes. However, as you will see from the examples I will mention, the computational cost is enormous, and still it will not be possible, at least for my lifetime, to be able to simulate the entire star for its entire lifetime in 3D simulations. So considering all the motions exactly as you'll see in some of those simulations. This is because the simulations must follow time steps. So it's how much of a jump in time can you make between two models of the structure of a star. And these time steps are of the order of 1 second to a few days, whereas, as I said earlier, the lifetime of stars is between millions to billions of years. So it's not going to be possible, except in my dreams still, to simulate stars in 3D simulations. So these are the main limitations. For the expert, you might want to ask me more details about the information at the bottom of the screen. Okay. I've got a message here that people have answered the question, but I'll keep the answers to my question for the break, if that's okay. So by doing this assumption of spherical symmetry, we don't need to worry about differences that are occurring on a sphere. We only need to know the dependence of properties like temperature and density from the center to the surface. So let's say if we divide our star into 1,000 points in the radial distance, then our star has 1,000 points, or 1,000 cells, as we call them, in one dimension. But in 3D, they would have 1,000 times 1,000 times 1,000, which would mean 1 billion cells or parts of the star that we have to consider. So that's why the 1D models are much cheaper. So they're much cheaper to simulate and much faster, and that's the order of hours for a model. So that means we can simulate the entire star from center to surface for the entire lifetime with time steps that are thousands of years, And we can also calculate different models of different types of stars. I'm going to talk about low mass stars, high mass stars, and so on. And by calculating lots of models, we're going to be able to compare these models to all the observations of different stars that we see in the sky. However, these 1D models have to approximate the processes like turbulence, rotation, and magnetic fields that are occurring in the star. So in a way, we can compare 1D models to this inflated cow, where things are roughly spherical, but we know that there are aspects like the horns and the ears of the cow that do not fit into our 1D approximation. And therefore, how can we improve models of stars, theoretical models of stars? We have to take our approximated 1D models to calculate the entire evolution of stars. When we notice that something is imprecise or incorrect, like the horns, we can do targeted 3D detailed simulations of that theory or process. Then we have to analyze it into a theoretical framework and then improve our model of cow horns to produce better models of stars. And then, so now we have a general way of modeling stars on computers. We have equations of physics that we can put into a computer program. We usually use Fortran and Python as programming languages. We now need a computer to run those simulations. So this is the prettiest and one of the most powerful computers I've used in my career. It's called Mare Nostrum 4. It's located in a church building in Barcelona, in Spain. And you can see this enclosure with lots of shelves, so lots of cupboards. And each of those cupboards has got about 70 computers, all piled up, so stacked up like this. And each of those computers in a slab is much more powerful than the laptop I'm using for this presentation. So just imagine there's about 50 cupboards. Each cupboard has got 70 computers, and each of those computers is more powerful than the laptop that we are using. So together, there are about over 100,000 cores, processing units. Okay, so using some of these supercomputers, we can then try to do some of these 3D hydro simulations. So these are detailed simulations. And for that, we use millions up to billions of computing hours. And this is just to simulate a small cube inside a star. So we call this setup a box in a star setup. So we're going to simulate a small box. We're going to go inside the star, see what's happening in this small box inside the star. So these simulations were done with a computer code called Prompi. And the movie I'm going to show you would have taken 85 years to simulate on the laptop I used for this presentation, but it only took a few months on a supercomputer in Durham. Okay, so let's look in more details what is simulated here. This is our simulation box on the right-hand side. So you see it's a 3D box, right? Like a cube. And the middle is going to be a turbulent, or what we call a convective region. And it's unstable because there's too much energy being produced at the bottom here by nuclear reactions. And then the top and bottom layer are so-called stable region. So they're supposed to sit still there, all quiet. And what the movie I'm going to show you is basically a view from the side. So just imagine you're looking straight into that box. What do you see at the side of that box? And you can see the boundaries between the turbulent and stable region that are here and there when we view it from the side, and the stable regions are here at the top and bottom. Okay, and remember that when we do 1D approximation, we assume that everything's the same on the sphere. If I take a box, so that means a small part of this, that means my 1D model is a straight line on this plot. And these 3D simulations are there to tell us how correct is this approximation that the boundary between the unstable and stable region is a straight line. Okay, so let's have a look at one of those simulations. So what you cannot see from the movie itself, but what I'm explaining to you now is that there is carbon fusion taking place. So two carbon nuclei, or many pairs of carbon nuclei, fusing together at the bottom of this unstable region. This releases a lot of heat, which heats up the gas and therefore makes it buoyant and go up inside the star. And you can see it here. Now the color in this movie represents the speed or velocity magnitude. So it doesn't tell you direction, but just by following which particles move fast, you can kind of follow the flow. And if you look carefully, you can see a gas or plasma, as we call it, undergoing circular motion, circular flows. But what we are very interested in is what's happening at this top boundary, right? Remember, the boundaries between the stable and unstable region. And in our approximate model, this is a straight line. And you see in the 3D simulation that it's very much, there's many more details. There's, for example, shear, so Kelvin-Helmholtz instabilities for those who know about this type of instabilities. You also see that there are colors in the top part, and this means that there are waves excited by the turbulent flow punching into that boundary, and that excites wave in the region where in 1D models we say nothing is moving. So we are learning with these new simulations more and more about turbulent motions inside stars. Okay, now I'm trying to go to the next slide. Okay, so these are some of the points I've mentioned. So instead of a simple straight line for the boundary between the unstable and stable region, we have a shape, deformed boundary with some mixing, some shear mixing happening, and some wave being excited at the top. And why do we care where this boundary is and what the properties of the boundary are? Is this region, as you saw, is fully mixed. But now the nuclear burning occurs only at the bottom of here. So if you mix nothing, then you burn your fuel and then your fuel is gone. You have nothing left to burn. But if this whole region is mixed, then you have a lot more fuel to burn. And for example, your star is going to live for much longer, the more mixing there is. Okay, so we've learned a little bit how we can improve our approximate models in 1D with 3D models. Let's now look at what we can do with the 1D models and how we can, how they teach us how stars evolve, what is their fate. So with these models, as I say, we can determine the structure of the star, not just at a given point, but throughout their evolution. So from the time they're born till the time they die. And the key property of a star is its mass. And the sun being our closest star, our main star, the sun is a reference. So we're going to compare the mass of stars to the mass of the sun. So we're going to use the solar mass unit. So the sun is obviously a 1 solar mass star. There are other key properties, which are, for example, the initial chemical composition and other properties like rotation, and whether stars are just single on their own or whether they have another companion nearby that will matter. But roughly speaking, these models can tell us how the sun evolves in time and what is the fate of the sun. So stars like the sun burn hydrogen into helium, and they do that for about 9 billion years. And the sun is a middle-aged star, so we have another 4.5 billion years of hydrogen burning into helium. Okay, and then once all the hydrogen is being converted to helium, this helium will burn into carbon and oxygen for another billion years. But this is not going to be a nice period for the Earth, because what happens when hydrogen is completely depleted, the core will contract under gravity, and due to this core contraction, the outer layer of the star will expand, and that will destroy life on Earth at that point. But just so that you're not packing your suitcase right now, know that we have another 4.5 billion years before this happens. So I think human beings are the main danger to human life. We have to look after our planet and avoid climate change and other things before the sun will change its shape or size. And because the outer layer will expand later on, the surface will cool down and the star will become red. So that's why they call red giant, large and red. Okay, further down the line, when helium is burned into carbon, the carbon-oxygen core, which can't do anything anymore, will become the white dwarf. And this is one of the stellar remnants that we've discussed. And so-called low mass stars like the sun, and also intermediate mass stars roughly between 1 and 10 times the mass of the sun, will never reach high enough temperatures to burn carbon. So therefore, stars like the sun will end up as a white dwarf in the center, and the high luminosity or light they produce will slowly peel off the outer layers, and they will produce very pretty planetary nebulae, as we can see them here. So this is kind of the fate of the sun, a white dwarf in the center with a pretty planetary nebulae around it. Let's move now to massive stars. These are stars more massive than about 10 times the mass of the sun. And like low mass stars, they burn hydrogen into helium, then helium into carbon and oxygen. But unlike low mass stars, they keep contracting and get hotter and hotter, and they get hot enough for carbon fusion to take place. Now, carbon fusion occurs by 2 carbon nuclei merging together and producing elements like magnesium-24 and neon-20. Then something slightly different occurs for neon-20. Neon-20 gets destroyed by a photon, so very energetic light, and emits an alpha particle, so a helium-4 nucleus, and produces oxygen-16. That helium particle can capture on another neon nucleus and produce again some magnesium. Next, when every single of these burning phase finishes, gravity is still there. So every time you finish burning stage, gravity compresses the star a little bit more, and every time you get a bit hotter and hotter. The next burning phase is oxygen fusion. Again, you take 2 oxygen nuclei, put them together, and you end up producing elements like sulfur and silicon. Silicon and sulfur are more like neon-20. They both get destroyed and produce helium-4 nuclei or capture helium-4 nuclei all the way up to nickel-56. Now, nickel-56 and the other elements around iron are some of the most stable nuclei among the periodic table, and therefore not enough nuclear energy generation can be extracted from this nuclear matter, and therefore this is the point where gravity wins. So the inner core, which is composed of iron, contracts until nucleons like neutrons and protons are so close together that additionally in falling matter is bouncing on this inner core. This launches a shock wave that ends up producing a supernova explosion. So you've probably heard the term supernova. So that's when you have the inner core, which later on will become a neutron star or possibly a black hole, and then this explosion of the outer layers. So this is called a core collapse because the iron core collapses before we have the supernova explosion. And if the star is about 10 to 30 solar masses, at the start we produce a neutron star. If the star is even more massive, it's going to produce a black hole at the end. Okay, so that brings me to the topic of supernova. And most supernova are so-called core collapse supernova. They come from massive stars. Observers have classified different types of supernova depending on the chemical composition of the ejecta. And for example, type 2, 1b, and c supernova are all coming from massive stars. There is one major exception, the so-called type 1a supernova that come from a white dwarf. So remember, those low mass stars like the sun produce a white dwarf, and they never get hot enough to do anything after that. But if they accrete more mass, they can overtake the so-called Chandrasekhar limit, at which point they implode and then explode by a thermonuclear explosion. So you can also have this low mass star dying as type 1a supernova. Let me just check the. No, I think it's about 30 past. I don't see the chat, and we said we would take a break right about now.
Okay, so welcome back, everybody. I hope those of you that have gone for a coffee or a tea have managed to get back in time. As agreed, Raphael is going to spend another 15 or 20 minutes going through the last of his lecture. Questions have come in. Raphael has got access to those now. He may answer them next, or he may answer them at the end. So stay tuned. If you have asked a question, we will do our very best to answer them, and I'll hand straight back to Raphael. Thank you.
Okay, thank you, Scott. I think the questions are too interesting, so I will not finish my talk if I start answering the question. I just discussed the guesses for the number of cars that correspond to the mass of a teaspoon from a neutron star, and we got lots of values from 10 to the 12 kilos, from 3, and somebody even guessed the number I usually give as an answer, which is 100 million cars. Okay, so just imagine if you could take a teaspoon out of a neutron star, you would have the same mass as 100 million cars. So these are pretty dense stars. I think you can still see my screen. So the next slide should be gravitational wave astronomy. And we live in exciting times where not only can we see stars and supernova explosions, we've been able to see neutron stars for a while if they emit pulsation. But now we have a new window on the universe called gravitational waves, which is ripple of space-time itself. And this enables us to determine, or to indirectly determine, the existence of many more black holes. And these are shown in blue in this diagram, showing the mass of the black holes, again, using the sun as the unit. So we see that we have black holes around 40 or 50 times the mass of the sun as end product of the evolution of stars, which is exciting because it's, as you can imagine, light cannot escape black holes, so it's very hard to learn information about black holes. So these gravitational waves are very useful to learn more about black holes in the universe. Okay, but the question we started with and we will finish with today is about how do stars produce the chemical elements that we are made of and the others. And for that, I need to give you a brief overview of the evolution of the universe. So this is the evolution of the universe summarized in one slide, where we start with the Big Bang on the left and end up as now on the right. So it took about 400 million years after the Big Bang for the first stars to form. And from that point, actually at that point, we only had hydrogen and helium created during the Big Bang early phases. So at that point, we only had hydrogen and helium in the universe. It wouldn't have been very interesting to form chemistry at that point. But from that point onwards, stars and massive stars in particular took this hydrogen and helium, fused it together to produce heavy elements all the way to iron. And we're going to see also later on how we can produce elements from iron upwards. They then exploded. So that means redistributed their products into the gas around it, into the other galaxies that also formed. And later on, new stars formed, produced new elements, explode, and therefore redistribute the elements, new stars form, etc., etc. So you have multiple generations of stars that slowly enrich the universe in the chemical elements that we can observe today now. Okay, so that brings us back to the periodic table. So you're all familiar with the periodic table, and in this table, the elements are organized according to the number of protons, or the so-called atomic number Z. And this is what matters for chemistry, because that also tells us how many electrons there are in those atoms. However, when we're talking about creating those chemical elements, and in physics in particular, we not only care about the number of protons that are inside atoms, we also care about the number of neutrons that are found in atoms. And therefore, we replace the periodic table by the so-called chart of nuclides. So here we again have the number of neutrons and number of protons. The periodic table would just be one box stacked up vertically in this diagram. And I've mentioned that stars undergo fusion from hydrogen to helium, etc., all the way up to iron, and iron sits roughly here in the chart of nuclides. Now, there are a lot more elements, and all the stable elements that we see on Earth are shown in black here. but the Coulomb force or the electric repulsion is too strong to allow fusion to take place above iron. So what happens instead is that the elements above iron are created by neutron captures. And we therefore have these processes called R for rapid and S for slow processes. And this relates to the pace of how fast do you capture neutrons on iron and other elements. So it's R for rapid neutron capture and S for slow neutron capture. And we're going to see that, well, I don't have time to talk about it in details, but the rapid process requires extreme conditions, which are either found in unique core collapse supernova powered by magnetic fields or rotation, or in neutron star mergers. So nowadays it's quite popular to explain the R process with neutron star mergers. On the other hand, the slow process takes place mostly in low mass stars, later on past the red giant phase, in what we call asymptotic giant branch stars. But in the last 10 years or so, I've also looked at how massive stars can produce the so-called weak S process, and this is starting from iron going all the way up to strontium by using rotation as a boosting ingredient. Okay, so by studying stars, how the universe evolves with all our models, we can then also use observations to compare to models. We can then color the periodic table according to which stars produce most of a certain element. So if we start with hydrogen and helium, as I explained, those are created during the Big Bang, so not in stars. However, if we look at elements like oxygen, you see that they're all yellow. This means that they were all produced in massive stars and ejected when we had this core collapse supernova explosion. And then you can pick your own element and ask me later, or look back at the different colors and find out where your favorite element comes from in terms of stars. So what is the star makeup of a given element? Now I'm going to show you a few different versions of those periodic table where their origin is explained, because this one is the one currently on Wikipedia, which has had significant contribution from a scientist called Jennifer Johnson, who kind of looked at the older version of Wikipedia where they were talking about big and small stars. But as I try to explain in this talk, if you look at stars like the sun, they start kind of small, and later on in their life, they become very big. So talking about the size of the star is not a very good way to understand the properties of stars. However, or on the other hand, talking about the mass of the star is a much better way of talking about different types of stars. So in particular here, we talk about massive stars, low mass stars, and the old Wikipedia version was talking about small and big stars, and now the new version has moved to talk about the mass of stars. The other version I'm going to show you next is, you see here that you have merging neutron star in purple that contributes a lot to many of the very heavy elements. And same here, so this is roughly the same origin for different elements. Merging neutron stars is in orange, so you see it's contributing a lot to silver and gold. However, more recent work by Chaki Kobayashi, a scientist at Hertfordshire University, has come up with a revised version of the periodic table. And this one also contains a bit more information. It includes information of time along the horizontal direction. So if you, for example, focus on iron 56 or iron, you see from left, this was the abundance at the Big Bang. And on the right is the abundance now, 13.8 gigayears later. And by looking at the different portions of the colored region, you can see which type of star process created most of the iron. So if we now look at iron, it's a combination of exploding white dwarfs, the type 1a supernova, and massive stars that produce the iron in our blood. And you can see in this plot, if you talk about silver and gold, it was mostly massive stars the exploding massive stars that produced silver and gold. So it's still an open question, which stars produced most of the gold and silver in the universe. And I think different versions in the future will probably still change the fraction of silver and gold that comes from different processes. Okay, you probably realize I talked about a lot of different aspects of physics. I've talked about stars, I've talked about galaxies, I've talked about nuclear reactions, observations, theory, modeling. So that means a lot of scientists are involved in answering this important question. And this is why we have to cooperate as different scientists at the country, so at the national level and also international level. And I spend a fraction of my week this week talking with colleagues who are part of the Bridge C network in the UK. So this is a UK network where we work together to answer the question about the origin of the elements. Since 2017, I also lead a European network called CATEC. It's a cost action. And all these networks connect the research that is taking place in nuclear physics theory, experiments, and then the modeling that I've described in this talk to models of galaxies and astronomical observations, so that together we can improve our understanding of this puzzle. And this will continue for another 4 years with the so-called CATEC Infra project at the European level. We also have a worldwide cooperation on the topic via the IRENA collaboration. Now, there are two projects that I would like to talk about on this topic. Is one, as part of the CATEC action, we created a calendar of women who made nuclear astrophysics. We have an online free version for this year, so 2021, and we plan to print out lots of copies for 2022. So we will try to contact as many schools as possible to really highlight the role that women made to nuclear astrophysics, to encourage young girls and women to continue playing a key role in nuclear astrophysics. And the other point I want to make is that we are going to develop masterclass. So these are activities for, let's say, 10 to 15-year-old students to learn more about nuclear astrophysics and also encourage them to study physics at universities. So if you're a school teacher, maybe you can contact me and help me on that project. Okay, so finally, it's about almost time. Let's answer the question, what stars are you made of? So on the left-hand side, you see the person, the drawing of the person I showed you at the start, with mostly oxygen, carbon, hydrogen. So now knowing where our elements like oxygen, carbon, and hydrogen are made, we can then estimate what stars we are made of. So roughly speaking, we are made of 74% of massive stars, 15% low mass stars, 10% we are relics of the Big Bang, so that's the hydrogen we are made of, and then 1% of us are traces of exotic stars like neutron star mergers, type 1a, supernova, etc., etc. But this small fraction is also the most interesting fraction. Okay, so thanks for joining, and while I'll answer the question, I will show you again the animation I started with. Okay, so Scott, you might come back online, but otherwise I can see the questions already. Do I just take them in order?
So Raphael, if you don't mind, I'm going to read them out for the benefit of our audience, and then if you could just answer them, that would be fantastic. It looks like we've got 5 questions, which will be perfect. If you do have any more, though, please pop them in the chat. If we can't get through them this evening, Raphael will answer them and we'll get them back to you via email. So the first question that came in was from Richard about half an hour ago, which says, do you have any limitations or simulation properties for the theoretical creation of quark stars?
Yeah, so quark stars, I mean, in one sense, neutrons and protons are made out of quarks. So you might be asking about strange quark stars or different phases of matter. So I think, and different phases of matter are in the inside of the neutron star. So it's not so easy to have a tight constraint on that. but there are people modeling the existence of, for example, strange quark stars. They're called sometimes strange stars, but there is no firm evidence for their existence.
Fantastic, Raphael. Right, question number 2, and this came in from Paul, so thank you, Paul. What would we observe from Earth if a star like Betelgeuse went supernova?
Okay, so I must admit I just Googled the answer just to have an idea of what are the ranges of answers on that topic. And one possibility, which would be the brightest possibility, would be that the Betelgeuse explosion would be as bright as the full half moon. So it would be very bright in the sky. But what would be even more interesting for me, and possibly one of the theoretical predictions that we would make, is that actually Betelgeuse will collapse to a black hole with almost no explosion. So instead of producing a very bright explosive end, it would produce nothing and disappear. That would be the most interesting and possibly my favorite outcome for Betelgeuse.
I think I'd have to agree with you there, Raphael. Yeah, fantastic. Okay, question number 3. It's not from me, although it is from another Scott. So thank you, Scott. The question is, when you program the computer models, what sort of programming frameworks are you using?
So I think I briefly mentioned that we use Fortran and Python programming languages. Supercomputers use Linux operating systems in general. And I think that's mainly it, Fortran and Python. So if you're wondering what would be a good programming language to learn, I would definitely try to learn Python because it's used in very different fields, not just physics, but any random context. Otherwise, between Fortran and C, this is pretty similar. But if you want heavy-duty computation, you can't just rely on Python. You have to use C or Fortran.
Brilliant. Cheers, Raphael. Okay, the next question is from Alex, and Alex asks, are you excited about the comet material that has just been returned to Earth, and what do you think we will learn from it?
Okay, I must admit I've not followed that news. I guess I was too busy marking and teaching in the last few weeks. In general, comets tell us it's kind of a new measurement of the composition of the universe around us. So I guess it depends how different the measurement will be from what we've already got. It might just be a confirmation, but in general, it's always exciting to have more material coming from space. So I'm in general excited.
Okay, right. Then we'll move on to a question from Andy. I noticed Andy, even Andy, a regular at our face-to-face talks. So this is quite a long one, so I'll try and abbreviate as best I can. If the universe is 13.7 billion years old, and our sun is 4.5 billion years old, then Earth is formed from stars that have lived and died before our sun was formed. That sort of suggests that our sun is only a second generation star, 9 billion years of age, and Earth was formed from first generation, unless earlier stars lived and died more quickly. The timeline seems to suggest it's too short to generate all of the planets and elements.
Yeah, so I only briefly mentioned that point in my talk, so thanks for asking this question. I said that stars have a lifetime between 1 million or a few million to billions of years, but I've only mentioned the lifetime of the sun as 9 billion years. As I said, massive stars have lived much shorter, so they only take about a few million years. So then you can have not 1,000, but hundreds of massive star generation in a billion years. So your point is very correct, what you mentioned. And the answer to that question is massive stars have short lifetimes that enable the production of the elements. But low mass stars can also contribute if there are other people who like low mass stars.
Excellent. Okay, I think we're into the final 2 questions, Raphael. This is a shorter one. Is our sun a second or third generation star? And how do we know that? That question comes from Paul.
Yeah, so what is very exciting is we can observe different stars, even though we don't see them evolve themselves. By looking at different stars, we see kind of different time or level of enrichment. and we can see stars in our galaxies that are much poorer in metals than the sun. And the poorer you are in metals hints at a star that of a previous generation or older generations. So for example, we observe stars that have 1 million times less iron in them. So we think that some of these stars were in the first few generations of stars, not the first, but maybe second or third generation stars. Whereas the sun is generation, I don't know, there's not a number, but it's definitely not the first few, it's a lot down the line.
Thank you for that, Raphael. Interestingly, we've got Professor Rob Jeffries, who I know you'll know well, who's posted to say it's third lead, apparently. Okay, interesting. I'm not sure what you responded to there, Rob, but thank you. The final question then, which has come from Alex, who says he loves the final slide, so we'll leave that one on there, Raphael. Which stars are you from? Can you expand on that? Surely many of the individual atoms were in massive stars which explode, and the debris forms smaller stars, and maybe the atoms are blown off, in the winds, etc.
Yeah, I mean, so your questions possibly, is the oxygen that is in our body been part of multiple generations of stars? And probably yes, I would say, because if you have a massive star, it's going to produce a few solar masses of oxygen, but then the massive star explodes. So these oxygen atoms are then spread across many more massive solar masses of gas. And then out of a small chunk of that gas, trying to stay in the screen, then a new star forms. If you already have oxygen and it's a low mass star, that low mass star will just carry the oxygen with it. And the inner part will stay in a wide dwarf, and then mass loss will blow away that oxygen. Then after that, most of that oxygen will not be changed that much more unless it ends up in the middle of another massive star where it could be burned to something higher like iron. But possibly the oxygen has been in many stars, but has only been produced by one massive star. Hope that makes sense.
Okay, thank you very much for that, Raphael. I think we are going to wrap it up. That was all the questions that we have received. So thank you to everybody that sent in a question. I'm just going to take back the presentation now, Raphael, if you don't mind, to show you. Brilliant. Just to remind everybody, hopefully you can see our programme. Our next lecture is due to take place on the 21st of January. So those that like an old-fashioned pen and paper, now's the time to get that out. 21st of January. The speaker is Dr. Mark Worley from the Institute of Physics. For those that are local, you'll know Mark. He was an ex-teacher, ex-physics teacher a long time ago, talking about Caroline and William Herschel. So that sounds like it could be a very interesting evening. For those that want something a bit before Christmas and you still haven't had your full fix of physics, some colleagues tonight at Keele are running an event on Monday. If you aren't aware, Jupiter and Saturn are going to be at their closest point in terms of how we view them from Earth in about 400 years. I think the last time they were this close was 1623. So get out there tomorrow evening, between now and say the 25th, about 6 o'clock in the evening. Look southwestward, you'll see two bright lights. That is in fact Saturn and Jupiter getting very close. And if you want to find out a bit more about that, we are running a radio show on the 21st with those details. If you haven't got time to write them down now, please just drop myself an email or a message and I will happily get back to you. So thank you very much, everybody, for attending this evening. I do wish you all a very Merry Christmas. Enjoy it in the best way you can. I look forward to seeing you all again in January. So thank you very much and good night.
Bye, Merry Christmas, Happy New Year.